Hi, I'm Tanay Narshana, presenting our work DFPC Data Flow Driven Tuning of Coupled Channels Without Data, done at the Indian Institute of Science along with Chaitanya Murti and Professor Chiranjib Bhattacharyya. This work was supported by AMD. Deep neural networks are difficult to deploy owing to their high memory requirements and inference latencies. Structured pruning aims to alleviate this issue without the use of specialized hardware or software by removing unimportant neurons or channels from the network. In this work, for the first time, we address the problem of pruning coupled channels in the data-free regime. To avoid issues like vanishing gradients, modern networks consist of complex interconnections between the layers, such as residual connections. Such layers are difficult to prune. To discard a neuron associated with a residual connection, one needs to remove multiple neurons simultaneously to avoid the network from breaking. Such neurons are said to be coupled. Most structure pruning methods do not prune coupled elements of the network. We observe that such layers consume more than 2/3 of the inference time. Thus, not pruning them is a loss of opportunity for compression. Existing works to prune coupled elements, however, are data-driven. But data may not be available due to reasons like privacy and maintaining competitive advantage. Thus, there has been a rise in the interest for data-free pruning. Coupled elements of a network lack proper characterization. Towards this end, we introduce data flow couplings or DFCs to precisely capture the notion of coupling in a network. Consider a subnetwork of ResNet50 as shown on the left. If we want to prune the output of layer 14, we need to prune everything that is colored red. We neatly represent this instance of coupling by the diagram on the center, which is an instance of a DFC in this network. A DFC consists of the feed-in layers whose outputs are coupled, the feed-out layers whose inputs are coupled, and the element-wise transformation functions F. It is interesting to note that DFCs also capture the notion of consecutiveness between layers. We say that the triplet ABF denoted by tau is a DFC if F consists of element-wise transformations, the data flow graph forms a single component, and no larger DFC is possible with these set of feed-in layers and feed-out layers in them. Now that we want to prune elements of a DFC, inferring their saliencies or importances may not be straightforward. We try to answer, can we infer saliencies of these elements using methods designed for single branch network? Our empirical experiments on 3 popular saliency mechanisms show that this may not be a good idea. This is because it is often the case that the feed-in layers significantly disagree regarding the importance of a particular element. Thus, we required grouped saliencies that jointly compute saliency using one or more of all the feed-in layers, the feed-out layers, and the transformation functions. We present the backwards graph-based saliency computation algorithm or the BGSC algorithm, which is our novel data-free saliency mechanism for coupled elements. Consider a DFC as shown and focus on the path between layers 14 and 16. We accumulate scores with the accumulator vector initialized as shown. As we traverse backwards on the data flow graph, we do nothing when we encounter a residual connection. When we encounter an element-wise transformation, we multiply the accumulator vector by the transformation's Lipschitz constants. Finally, on reaching a feed-in layer, we compute the accumulator score along the path pi for neuron k as shown. For channel k of a DFC tau, we take the saliency to be the summation of L1 norm of all scores obtained from all paths between the feed-out and the feed-in layers. We show that the sum of L1 norms of perturbations of outputs of the feed-out layers on pruning the kth neuron is upper bounded by gamma times the saliency for some constant gamma. Note that this saliency computation does not require training example. Our empirical results on the data-free regime show the merit of pruning coupled channels since they attain better inference speedups for similar accuracy. Moreover, our pruning strategy DFPC shows up to 83% more parametric sparsity in the data-free regime. If we allow to fine-tune, DFPC still outperforms our baselines with respect to speedups, particularly 3net by 47.1% with a 2.2% more accuracy and Greg2 by 49% for similar accuracy. To conclude, the key takeaways from our work are coupled channels are important to prune and lead to better inference latencies for similar accuracies. One requires group saliencies to prune coupled channels. The DFPC pruning strategy demonstrates strong empirical results as opposed to baselines in both data-free and data-driven regimes. Thanks for attending our virtual presentation. We look forward to meet and discuss about sparsity in person at Kigali.